Hi everybody, this is log page 12 and today we're going to be talking about adding and subtracting radical expressions. Our objective for today is to simplify radical expressions involving addition and subtraction. We're going to be simplifying first of all with like terms. I'd like for you to think back, if you will, to algebra, or not to algebra 1, but to math 1. And I'd like for you to recall problems that look like this. 3x plus 6x minus 2x. And I want you to remember that when we did these kinds of problems in math 1, that what we did was we added like terms. They had to all have the same variable, and we were then able to add the numbers in front. We could add 3 plus 6 plus negative 2, and there were 3 plus 6 plus negative 2 x's here. 3 x's plus 6 x's plus negative 2 x's. This gives me 3 plus 6 is 9 plus negative 2 is 7 x's. And this is called combining like terms. And this should be a tool that you have in your toolbox from Math 1. Now what we're going to do is we're going to use this particular example of combining like terms to combine like radicals. If I have radicals that have the same index, and remember the index is the little understood number here. This is an understood 2, an understood 2, an understood 2. The same index and the same radicand. 11 is the radicand. That's the number or the expression under the radical. So like radicals, oh, is that going to fit? Yes. Like radicals have the same index and the same radicand. Same index and the same radicand. So like radicals have the same index and the same radicand. If they are like radicals, they have the same index and the same radicand, then we can combine them just like we did in Math 1, combining like terms. We can say 3 plus 6 minus 2 times the square root of 11. 3 plus 6 is 9, minus 2 is 7 square roots of 11. Okay, the next problem, simplifying with like terms, we have 9 square roots of 7 minus 4 square roots of 2 plus 3 square roots of 2 plus 5 square roots of 7. What we're going to do next is we're going to look for the ones that have like radicals. So this 2 is the index, the 7 is the radicand. So the 9 square roots of 7 is like the 5 square roots of 7. Let me move this over so you can see it. The 9 square roots of 7 is like the 5 square roots of 7 because the index is the same and the radicand is the same. So I can move them together. 9 square roots of 7 plus 5 square roots of 7. The negative 4 square roots of 2 and the positive 3 square roots of 2 are like radicals because their index is the same and their radicand is the same. So I can put them together. Negative 4 square roots of 2 plus positive 3 square roots of 2. And now I can add my like radicals. So I'm going to add 9 plus 5 times the square root of 7 plus negative 4 plus 3 times the square root of 2. 9 plus 5 gives me 14 square roots of 7. Negative 4 plus 3 gives me a negative 1 square root of 2. Now there's an understood 1 right here. You don't have to write it, but it's a little understood 1 that fits right in there, the little ghost 1. Some very, very important information. If each radical in a radical expression is not in simplest form, then we have to simplify them first. Then we can use the distributive property whenever possible to further simplify the expression. We must simplify first if it's not in simplest form. Okay, let's look at an example. Now we're going to be simplifying with unlike terms or different radicands. So I have 7 times the square root of 98 plus 5 times the square root of 32 minus 2 times the square root of 75. These radicals do not have the same radicands. Now in this PowerPoint, what we've done right here is we've used our patterns that we looked at 2 days ago, and we have tried to come up with the largest perfect square factor for each of these radicands. If you can see this, and you can see that 49 is a perfect square, and we did 49 times 2 to get 98. And if you can see that 16 is a perfect square, and we did 16 times 2 to get 32. And if you can see that 25 is a perfect square, and we did 25 times 3 to get 75, then you don't have to necessarily do the factor trees. But if you don't see that, then you do need to still come over here and do your factor trees. 2 times 49, and 2 is prime. 49 is 7 times 7, and 7 is prime. So this is 7 on the outside times 2 times 7 times 7 on the inside, plus 5 on the outside, and then over here I'm going to do 32. 32 is 2 times 16. 2 is prime. 16 is 4 times 4, and 4 is 2 times 2, and 2 is prime. 4 is 2 times 2, and 2 is prime. So I have 1, 2, 3, 4, 5 2's. So 1, 2, 3, 4, 5 2's. Minus 2 times the square root of 75. I hope I'm going to be able to squeeze all these in here. 75 is 3 times 25. 3 is prime. 25 is 5 times 5. And those 5's are prime. So I have 3 times 5 times 5. And now, if you are doing the factor trees, you remember you're going to be looking, let me slide this back over, we're going to be looking for pairs. So this pair comes out as 1 and joins this 7 on the outside. So I have the 7 that was already there times the 7 that gets to come out times the square root of 2. Plus, I have 2 2's here, 2 2's there. This 2 doesn't have a partner. So this set of 2's gets to come out and join the 5 that's already there. This set of 2's gets to come out and join the 5 that's already there. And this little 2 has to stay under the radical. And then over here we've got a set of 5's under the radical. So they get to come out and join the 2 that's already outside, and this little 3 must stay under the radical. Now I can multiply. 7 times 7 is 49 times the square root of 2. 5 times 2 is 10 times 2 is 20. So plus 20 times the square root of 2 minus 2 times 5 is 10 times the square root of 3. Now I can look to see which ones are like radicals. The square root of 2 has the same index and the same radicand. So this 49 square roots of 2 plus 20 square roots of 2 gives me 49 plus 20, which is 69 square roots of 2. The square root of 3 is not like the square root of 2. Their index their indices, which is the plural of the word index. Indices, that's the plural of the word index. So their indices are the same, but their radicands are not the same. So these are not like radicals, and I can't combine them. So I just have to stop and leave my answer as 69 square roots of 2 minus 10 square roots of 3. Simplify your answer, then use a calculator to verify your answer. So on this one, we're going to look at 3 square roots of 7. Let's move this over. Minus 2 square roots of 28. 3 square roots of 7. Well, 7 is already a prime number, so I cannot do anything with that 7. The 28 I can see is 4 times 7, and 4 is a perfect square, so I could use 4 times 7. If I don't see that, then I'm going to come over here and do 28, which is 4 times 7. 7 is prime, and 4 is 2 times 2. And 2 is prime, so that's going to be 2 times 2 times 7. 3 square roots of 7 minus 2 is already outside. These two 2's get to come out and join it. And then the square root of 7. 3 square roots of 7 minus 2 times 2 is 4 square roots of 7. And this gives me 3 minus 4 times the square root of 7, which is negative 1 square root of 7. Now, if you want to put the 1 there, you certainly may. But if you don't want to put the 1 there, then you don't have to. I want you now to get out your calculator and let's verify this. Okay, taking my calculator and turning it on. Slide it up just a little bit. Pull this up just a little bit. All right, I want to know if this is the right answer. So I'm going to type in negative square root of 7. Okay, the negative sign is right down here next to the decimal key. So there's my negative sign. The square root is right here above the x squared. You can see it in blue here. So I have to hit my second key and then my x squared key to get the square root. And then I'm going to type in 7. And then I can either arrow out from under the radical or hit enter. And that gives me negative 2.645751311. I'm going to round this to the hundredths place. So negative 2 and 65 hundredths. Now how do I know that that's the right answer? Well, the next thing that I'm going to do is type in the problem that I started with. So 3 square root 7, arrow out from under the radical, minus 2 square root 28, arrow out from under the radical. This is the problem that I started with. And if the problem that I started with is the same as my answer, then I know that I've done this correctly. So I've checked my work and I know it's right. Okay, I want you to look through this problem, copy it on your paper, see if it makes sense to you, and write down any questions that you may have about this particular problem.